On the air. Oh, there it goes. And welcome this week to Absolute Zero. I am Rachel Appel.
I'm Bertrand Leroy, and today we are talking about causation.
Causation. So what causes something to happen?
Yeah, and it's trickier than it seems. A lot trickier.
I don't know. I hear alcohol causes lots of problems.
Oh, yeah. Well,
we're going right into causation.
Yeah, many things are caused by lots of different causes, and we have this tendency to attribute one single cause to a complex course of events.
Yeah.
I mean, when there are tragic events in particular, we are quick to blame one single thing for something that is actually a lot more complex. But in the context of science, it's quite difficult. And one of the things we should probably talk about is how causation and correlation are different, in a sense, because we hear, well, oftentimes somebody makes an argument and somebody else answers, yeah, well, correlation is not causation.
Right.
That is true, but what does it mean, right?
Yeah, I think it's become a handy excuse for some people. I mean,
yes,
like you said, it's true sometimes, but sometimes it's not. And things are not necessarily, again, that simple.
Yeah, and sure, you can find all kinds of weird correlations that are obviously not, that don't have a causal relationship.
Right.
And there is even a website devoted
Various
to that.
Correlations.
Yeah.
It is hysterical. I love that.
Yeah, I love it. But, sometimes correlation is actually an indication that there is causation, and we don't want to be too fast to dispel that, because otherwise we might actually miss some non-obvious causal relationships that are there.
Oh, so here's some good ones from spurious correlations.
Oh yes, please.
Per capita cheese consumption correlates with the number of people who died by becoming tangled in their bed sheets. First of all, the fact that there are people who died by becoming tangled in their bed sheets. Evolution is working, apparently. Taking out the bottom rung. Okay. Yeah. Total revenue generated by arcades correlates with computer science doctorates. That might actually...
That one makes sense.
That makes sense.
Yeah, so correlation is statistical interdependence, right? It's when we notice that the probability of one thing happening looks exactly like the probability of some other thing happening, right?
Right.
And causation is a kind of correlation. You cannot have causation if you don't have correlation, right?
Right.
But how do we determine the subset of correlated things that are actually related by a causal relationship? Is it that one happens before the other? That seems necessary, right?
But yeah, you have to have that, right, for something to be a causation.
Maybe we'll get back on that, because there are cases where it's not that obvious. Okay. But in most cases, in most cases that we deal with on a day-to-day basis, yeah, that is true. You would have to have the cause happen before the effect. Otherwise, are we really talking about causation? But even if we have that time difference if we know which one is happening before the other. It's still very tricky based only on statistical data to determine if there is a causal relationship.
Right. Well, because if you take a look at spurious correlations, yes, that's actual statistical data.
Yeah, so how do you make a difference? And oftentimes you make a difference by actually doing some experimentation. So you recreate the assumed cause, and you try to see if the assumed effect is actually happening.
Yes, kind of like the link of smoking and cancer.
Yeah,
we've kind of got some strong links to that.
You need to isolate variables and do all the science stuff, right?
And they've done that a long time ago.
Yeah, for smoking, yeah. But in general, that a large part of experimental science is actually doing exactly that, eliminating variables and trying to isolate the causal relationships and extracting some kind of model out of it. But when something has correlation or seems to have correlation, but there is no causation, how do we, where can that come from? It can be chance, which seems to be the case in all those spurious correlation.
Right.
The idea here being that there is so much stuff happening that you will have part of the stuff looking like some other part of the stuff. So it's just a matter of looking in the right place, and you will find something.
Right. It's statistically kind of like when people talk about dreams coming true or predictive dreams. If you think about the number of people that have ever been on Earth times the number of times they dream average per night, you're bound to dream something that will come true. I've even gotten fortune cookies that have come true. So
yeah, and you eliminate
they're not even fortunes. But
and you only keep the hits and you eliminate the misses.
Yes, precisely. So the whole rest of every other dream you had, none of that's coming true. But this one did, so dreams come true. Right?
Yeah. So that's basically the sharpshooter fallacy, where you draw the target around.
Yep.
Or it can be, selection bias and stuff like that.
People kind of make a causation and correlation out of that, those kind of things.
Yeah.
Yep.
So another possibility is that both events are correlated, and they are correlated because there is an underlying common cause for both of them. So you have two events. They are correlated, but there is a third one that you're not seeing that is causing both of them. So there is a causal relationship, but not between those two, but between those two and those two. So that's another possibility. But in that case, here's an example. If you throw a rock into a lake, you will have waves propagating, and the waves will hit the shores. So the event of this part of the wave hitting the shore on that part of the lake, and this part of the wave hitting the shore on that part of the lake, those two events are correlated. There is not one causing the other, but there is a common cause, which is me throwing the rock into the lake. So the way you can differentiate here is that you could create waves on one side and see if you have the exact same correlation. And then you can recreate the rock throwing and notice that in this case, you can actually reproduce exactly what you're seeing on both ends of the lake. And there are cases where you have a correlation that is entirely non-causal. So there is an actual correlation. It's not just chance, but the correlation, there is no causality relationship in the correlation. An example of that is that the surface of a square is correlated to the length of its sides, right? If you change the length, you change the surface, and if you change the surface, if you want to change the surface, you have to change the length, right? But you cannot say that the length is causing the surface. It's
right.
That's not true. And in this case, you don't even have a time. There is no time in there. It's just mass.
Right. It's just data.
And the last possibility is that there is an actual causal relationship, right? Pushing an object causes it to accelerate. Drinking battery acid causes death, and so on.
Yeah.
So yeah, those causal relationships had to be proven through some experimentation after noticing a correlation, right? Because if you don't know, well, battery acid, if you don't know that, you might accidentally drink it. Also, that seems unlikely, but I suppose that might happen. And you would notice that people die. So
at that point,
you only have correlation. But if you investigate, it's easy to find that there is an actual correlation there. Yep.
Yeah, I think people mix it up a lot. They'll either find causes where there's not, or they'll go into the, correlation doesn't equal causation when somebody brings up a valid point and there might actually be some links there.
Yeah, but it's surprisingly hard to
come up with causation. That. Yes. Yeah.
Yes. And this is probably because if you go to the fundamental physics of causation, things get actually kind of weird and even more difficult to understand.
Really, in physics? No way.
Yeah. Well, even the simple concept of one event happening after another, that is not that.
Yeah, once easy. You get down to like a quantum level,
so we'll get to
apart.
Yeah, we'll get to quantum events, which are even weirder. But I'm going to talk about relativity.
Okay.
First, so when you have two events, we know that because of relativity, time can happen differently depending on how things are moving, right?
Okay.
So if you're in one referential, you might have the time between two events can be different from that same time measured in a different referential. So in a referential that is moving relatively to the other. And if there is a condition for two events where if you go to certain speeds, if you go fast enough, if the difference between your referentials is fast enough, you will actually reverse the precedence of the events. So one event that seemed to be happening before the other will actually happen after the other. And in those cases, there can be no causality between those two events because their time relationship is actually not well defined. There is nothing absolute. But now, between events where there is a causation, those will always be within a region of space-time that will not change the succession of events, no matter what transformation you make between the referentials. So events that are related by a causal relationship are going to have the same succession of events, no matter what referential you're looking at.
Okay.
And you would have to go faster than light, which is impossible if you wanted to invert those events in time.
Interesting. Okay. Yeah, once you get to that part where it starts falling apart and things are all different.
Yeah. And in relativity, if you want to say that two events happened at the same time, they need to happen at the same place as well, because otherwise it's ill-defined what at the same time means.
Right.
Because you just have to move for the times to change. So simultaneity is only defined locally. It's not defined globally.
What you're describing kind of reminds me of Asimov's End of Eternity when you're talking about the 2 points in time and how they can switch. I kept thinking about the kettle that's in that story.
I don't remember that one.
It's about time travel, and they have this thing called the kettle in which they can go through to any point in time. It's kind of interesting.
Okay. What color is the kettle? Just
I don't know.
It's not black.
It's the kettle, whatever color they made it. That's what they called it. I don't think that it actually looks like a kettle.
Yeah, so you were mentioning quantum physics earlier. And that's even more interesting because as far as we know, there are events in quantum mechanics that are uncaused. There is no cause at all.
Okay.
For example, when an atom disintegrates, it just happens. It's it's like when you measure something and you get a result that is the probabilities are well defined, but which one value you will get is not predictable in advance. So an atom disintegration is exactly like that. You know the probability that it will decay, but you can't predict when.
Okay.
And this is actually how you build an actual random number generator. You use physics for that. So yeah, there are events that are uncaused, which is causing a lot of confusion to a lot of people.
Yes. Well, not to mention, as being humans, we tend to look for reasons behind things and causes behind things. We're all about causes and reasons. So
yeah,
when you don't have one, it makes us a little anxious.
Yeah, it's very unnatural for us to consider even that possibility. There is this famous argument that it relies on the assertion that all events have a cause or something along those lines. And no, that is not true. And the universe itself might actually be one of those uncaused phenomena. It's a little early to say that, but it might be the case. Yeah. So yeah, causation in quantum mechanics is even more complex to define. And
well, to be fair, everything in quantum mechanics is really more complex to define. I mean, there's that.
Yeah, common sense doesn't help much with this.
No, not at all. It's the least intuitive of the sciences, because everything you think you know is just completely inaccurate and upside down.
Yeah, common sense is actually an obstacle to your comprehension of what's really going on, which is counterintuitive.
Very counterintuitive.
Yeah,
I mean, a lot of science is, but in general, but in specific, physics and quantum mechanics are very counterintuitive, I think.
Yeah, but you know, there is this. We should talk about that sometime, about common sense and the place of common sense in science, and how can it be that common sense actually fails, because it seems like this thing that should always work, right?
Right. Well, it does in certain areas and on certain levels. Things make sense, but that's kind of what a couple of scientists, I think Dawkins calls it, Middle Earth. This kind of space that we live in as humans, we can apply common sense because we evolved to use that to survive. But when you get to these different levels where you're talking about, where you would hit space with the giant numbers or the tiny numbers that we are not used to dealing with, then common sense is not, it's out of that realm, right? So it's not very common out there.
Yeah, that's a really good point. And there is this thing about the laws of physics that are mostly local and reversible in time.
Mm-hmm.
And we'll do a show about the second law of thermodynamics, because I know that this is the objection that most would give to this. But if you look at the fundamental laws of motion of pretty much anything, the time variable is always reversible in those equations. So why do we perceive time going in only one direction? That is a problem that is actually quite tricky and could be the subject of another show. But yeah, if you have a time variable that is so easily reversible, how do you define causality in such a world? So relativity actually does help a little bit with this, because it does define what classes of events can have a well-defined relationship in time, but it is tricky. And are we limited in our perception of time because we our very functioning depends on time? We can only reason and function because we have memory, and memory is essentially what memory is there is this
personal
thing,
measurement of time.
It's breaking that symmetry. It's something that is staying in one state after a point in time. So you have an undefined state before, and then you have a well-defined state that continues forward in time. And this is basically saying that memory is irreversible. It's an irreversible phenomenon. So it's only possible if it relies on something that is irreversible. Which means that we can only exist in a subset of space-time that where the second law of thermodynamics is true.
Hey, coincidentally, that's kind of where we live.
Yeah, we are the Douglas, Douglas Adams puddle that wonders why the shape of the ground is so perfectly adapted to its own shape. Well, yeah. So yeah, we are creatures of time. So we perceive time in a very specific way, which gets in the way of understanding how time works at a fundamental physics level. And if you step back and look at the universe as one big space-time thing, then time becomes a very different thing. It's even more difficult when you consider the origin of the universe and what might happen to time there. And there are variations of cosmological ideas where time ceases to exist when you get close to that region. And if there is no time, there is no causation. So
right.
You can't even say that the universe comes into being, because that implies time.
Right, literally nothing is happening there if there's no causation.
No, happening is meaningless because there is no time, so no causation.
This is where a lot of our concepts become meaningless.
Yes. So the way you actually deal with those concepts is that you figure out what the equations are that rule the physics in those regimes, and you solve the equations and you try to extract some you try to articulate something out of that. But sometimes the real comprehension can only come from looking at the math.
Mathematics.
And common sense is not going to help you. When there is no time and no causality, then common sense is just out the window.
There's no common sense.
Yep. But the math doesn't lie.
Nope.
Okay. Well, that's That's all I had about causation.
Okay. That's all. I didn't have anything else.
Cool. That can be a short one.
Okay. Nice easy week this week.
Yeah. It's been a while, actually. We skipped a few weeks. And we might also use a few canned episodes in the next few weeks. We'll see.
Okay.
Cool. Well, thanks.
Until next week.
Until next week. Bye, everyone.